Do you have any question regarding last lecture? Does anybody has any question? Because we were using Hamilton's principle to obtain the Euler-Lagrangian equation using variational principle. So what we discuss variational principle in general, and one application of variational principle, I showed that shortest path between 2 points on a plane is a straight line. This we proved. Then same variational principle we use for Hamilton's principle using the Lagrangian and action. Then we obtain the Euler-Lagrangian equation. So that was and then I discussed couple of properties of Euler-Lagrangian equation. So do you have any question on this? Otherwise, then I'll go to the today's teaching. Can you see the whiteboard?
Yes, sir.
Okay. So we obtain from Hamilton's principle. What happened? Can you see the whiteboard?
No, sir.
Okay, okay. So I don't know, something happened. So let me check. Can go to the application. Somehow I gone out of meeting. So let me enter the meeting from my iPad. I have JQ then hyphen NKVU then hyphen T. NKVU VJQ. Just wait a minute. Something wrong. Let me VJQ. Okay. So now I should go to the sharing, and somehow I don't know why that one. Okay. No, these people, they are bothering. Okay. So Hamilton's principle, and I hope everybody has understood Hamilton's principle, implies Euler-Lagrangian equation, and this equation is written as, if your Lagrangian is function of, let us write now all variables. That time I use only 1 degrees of freedom. Now I use s degrees of freedom, I equal to 1 to s. Then Euler Lagrangian equation d dt of del L del Qi dot minus del L del Qi equal to 0. Okay. Okay. So this was the equation. So if I know the Lagrangian, then I can find the equation of motion. And we have found seen in as an example that if I have a equation Lagrangian of x dot square minus half k x square terms, then this will lead to my harmonic oscillator m x dot plus k x equal to 0, which is a simple harmonic oscillator. Okay. So now we are learning the properties of Lagrangian. So three properties I already mentioned. If you have L prime equal to L plus C, where C is constant, or if you have L prime equal to C times L, then it will describe the same system. So L prime and L will describe the same system. Okay. So now today I'm going to tell you another properties which is very important. Two of the properties are very important. Now if you have a L prime, which is like your L plus df dt, which qi and t, then what will happen? This is a very important. This is a total time derivative of a function which is function of coordinate and time, no velocity. So notice no velocity. In f. Then also I'm going to show that L and L prime will describe the same system. This is also true for this. Now this needs proof, and I'm going to prove this. Okay. So let us prove. So if I go to the action, so let me action for this is I prime, which is L prime dt. So initial time to final time. This is the line integration. So I prime is your L prime dt, where this. So let us calculate, and we can do this integration for this part very easily, because this is total time derivative. So this is basically your L dt dt, t initial to t final, plus integration df dt dt, right? T initial to t final. Okay. So let me erase the top part. Okay. So perform this integration of this part. So I can write now I prime is your I, because I is the action for L. So this is L dt. So this is L, plus this will be integrated df dt dt, right? So it is will be integrated. So it will be f q I t, but you have to calculate between t initial and t final. Okay. So this will be I. No, I use I or S action. I forgot the notation. Did I use I or S? Okay, don't
So
bother
S.
about. Yes, don't bother about. The other day I use it is S prime, and then this is so S prime equal to S plus this, but doesn't matter. This is notation. Some people use I, some people use S. So I forgot what I used last time, but anyhow, so if you have so we'll stick to I today. So if you have I, and then this quantity F Q final T final minus F Q initial T initial. Okay, this is I calculate this. Now what will be delta of I prime equal to delta of I plus, this is a function of QF and TF. This is a function of QI and TI. Remember, this is the variation, this is the initial point TI, QI point, and this is final point TI, TF, QF. So we are looking at all paths between these 2 points, but here there is no variation. Delta Qi is also 0, delta Qf is also 0. So no variation. So this is also only function of Qf, Tf. So the Qi and Ti, Qi and Qf does not change with time. So this variation will be 0. So delta I equal to 0 is the Hamilton principle, will implies delta I prime is also 0. So if I have, so now conclusion is that, now if I have two Lagrangian which is differ by a total time derivative of a function which is function of coordinate, generalized coordinate and time. No velocity dependence. If there is a velocity dependence here, then this will not work. These properties will not work. Okay. So this is a very important properties and very useful, that we'll see later. Okay. So now we are in the third properties, and let us finish the remaining properties. But before that, let me give you an example of that. Later I'll give you many examples of these properties. Also in the almost every year in the exam, I give a problem based on these properties. So that is why it is very important. So suppose I have a Lagrangian L, which is half m. So this is the only Lagrangian we know. So half k x square. And then I have L prime, say L plus ddt of say 3 x square plus 2x plus 1, some function. Now find now you find equation of motion for both L and L prime to show that it is, both cases to show the that it is simple harmonic oscillator for both cases. Okay, so this is there. This equation you have already obtained, no need. L prime equation of motion, you just make a derivative and then obtain the equation motion using Euler Lagrangian equation, and you will get the same equation of motion. So this is very interesting. This Lagrangian and this Lagrangian is different, non-trivially different, not like multiplying a constant or adding a constant. Okay, now let us go to the properties 4. Suppose I have a Lagrangian Qi dot and T, but it is supposed to depend I equal to 1 to s degrees of. So Lagrangian is function of s number of generalized coordinate s number of generalized velocity and t. But suppose there are a coordinate qk, suppose there is a coordinate qk such that del L del qk is 0. If it happens, suppose, okay, then this coordinate, then qk is called cyclic coordinate. It's clear that I have not complete these properties. What is the properties? But I'm explaining the properties that if you have a Lagrangian which is supposed to depend s number of coordinates because system has s degrees of freedom, but a special cases it may not depend on some of the coordinates. Suppose it does not depend on the qk coordinate, then qk is called cyclic coordinate. It may have a 1, it may have a 2, it may have a 3. I'll give you an example of cyclic coordinate. Okay. Cyclic coordinates are very important. So these two properties I am discussing today are very, very important. So cyclic coordinate, suppose I have a Lagrangian, two variable, q1, q2, q1 dot, q2 dot. Okay, two variable Lagrangian, and let me give you the Lagrangian half m q1 dot square, q2 dot square plus half k q1 square. It depends, it's supposed to be a two variable system, depends on two velocities q1, q2, but only one coordinate q2. So q2, so you can find that del L del q2 equal to 0. So q2 is cyclic. So this kind of coordinate is very important. Why? Because go back to the suppose equation of motion. So suppose equation of motion, I'm going to equation of motion for q2 variable. So it will be dd del L del q2 dot minus del L del q2 will be 0, right? For q2, this will be the equation. Okay, this will be the equation. Okay, now this term is 0 because it is cyclic, so this term is 0. So you find that del L del q2 dot is conserved or constant of motion. Right? Because ddt of del L del q2 dot is equal to 0. Something total derivative is 0 means that is a conserved quantity, does not change with time, or constant of motion. Constant of motion means as time evolves, it does not change. So this quantity is very important in that sense, that it does not change. I found a quantity which does not change. So in classical mechanics, our idea is to find whatever quantities involved in our theory, how they change with time, that is the dynamics. So in classical mechanics, we are interested to find how our momentum is changing, how particle velocity is changing, how particle position is changing, that we are supposed to know. But if I found some of the quantity does not change with time, then my job is for that coordinate is done. And this coordinate, this quantity is defined. So let me write 3 line, is the P2, which is called momentum conjugate to Q2. So momentum conjugate to Q2 or PK, QK will be del L del QK So whenever we have a cyclic coordinate, this property says that its momentum conjugate will be constant of motion. So if I have a cyclic coordinate, we don't have to do anything. We have to say that, oh, its momentum conjugate is constant of motion. So I can double derivative with the momentum and then can get a force, etc. So this is simple. So, okay. So whenever you have a cyclic coordinates, momentum conjugate is conserved quantity. Okay, so this is all about the properties, and I remind you that one more properties I used other day, which was the if you have more than one system, then Lagrangian you can add up. Right? So suppose I have a system A, I have a system B. This system is given by the Lagrangian LA. This system is described by Lagrangian B. Then this combined system will describe by Lagrangian LA plus AB if they are not interacting. If they are interacting, so this is for non-interacting. And L should be LA plus LB plus LAB if this is the interaction part of the Lagrangian. Okay. So this properties is also, so let me write this is fifth, the last properties, but this properties is also extremely important. Suppose I have two charge particles. Two charge particles suppose I have. So what will be the Lagrangian? I know the Lagrangian of one particle, its kinetic energy minus potential energy. Second particle also I know, if they are free, then so two particle, so two free particle, say mass, two free particles. So Lagrangian will be L1 and L2. So first particle Lagrangian in L1, second particle Lagrangian L2. So two free particle Lagrangian will be just sum of the individual Lagrangian. Now if they are charged particle will interact electromagnetically, the Coulomb's law. So then you have to add the Lagrangian for the two particle. Lagrangian corresponding to the considering first particle is free. Lagrangian considering the second particle is also free. Then this Coulomb interaction, this will give you the total Lagrangian. So in many cases you have many two particles, three particles, two pendulum, three pendulum, etc. So it will be very useful that individual Lagrangian you find first, add them, and then interaction term you add them, you will get the full Lagrangian of the system. Okay, so this is the all properties. Now we'll go to the how to construct the Lagrangian or a system. So how to construct the Lagrangian, or what will be the Lagrangian, that we are going to see. We saw one example of harmonic oscillator, and there we saw that Lagrangian is like a kinetic energy minus potential energy type, but that we'll going to see. So now we going to calculate, construct the Lagrangian.
सर
हाँ
सर प्रॉपर्टी 4 से सर एक क्वेश्चन था
हाँ
सर
बताओ।
उसमें सर जो आप कॉन्जुगेट मोमेंटम को कंजर्व सर बताएं सर, उसका कोई एक फिजिकल एग्जांपल सर नेचर में सर जो हो रहा हो बता सकते हैं?
हाँ हाँ वो बताएंगे, अभी थोड़ी देर रुक जाओ। फॉर एग्जाम्पल दैट, क्योंकि हमने जो एग्जाम्पल बताएंगे उसमें आपको लग्रांजियन लिखना पड़ेगा फिजिकल सिस्टम के लिए। तो अभी लग्रांजियन कैसे लिखा जाता है अभी तक नहीं मालूम, तो इसीलिए हम एग्जाम्पल नहीं दे रहा है। लेकिन आप अगर पूछ रहा है, जैसे आपको सेंट्रल फोर्स फील्ड, आप थोड़ा बहुत केपलर्स प्रॉब्लम पढ़ा है, तो यू हैव स्टडीड द केपलर प्रॉब्लम। For central force means the force, the potential does not depend on the angular variable theta, right? That is why it is, if the potential is only function of r, then it is called the central force. So it does not depend on theta, another variable. So theta is cyclic for central force motion. And all central force motion, angular momentum is conserved. So this is a physical example of cyclic coordinate. In central force motion, angle is a cyclic coordinate and angular momentum is conserved because of these properties. Okay, but I will not write the Lagrangian for a central force problem. I'll first construct the Lagrangian, and later we'll consider many places we'll find and we'll tell you that this is cyclic coordinate and this corresponding conserved quantity. Okay. Okay. So construct Lagrangian, and for that we'll consider only a free particle. So simplest possible particle. So free particle. Free particle means it don't interact with anybody, and free particle there's no force acting on it. So free particle can be at rest. So it doesn't give you anything so trivial. Or free particle can be in the uniform motion. That means if you are moving toward a particular direction all the time. So this is free particle. So this, oh, I don't know what is happening to this. Okay, so this has certain features. The particle, free particle has certain features. A particle moving, so system of free particle has certain features, certain properties. So let us first write down those. So Lagrangian, in principle, Lagrangian of a free particle in 3 dimensions. So in principle, according to our understanding, it should depend on R. Now I am using Cartesian coordinate as my general coordinate. It is 3 dimensional. So it may depend on R, it may depend on velocity, and it may depend free particle. So it may depend on time also. So a free particle have position, it has velocity, and the different time also. It may not depend on explicitly, but in general, this will be the possible Lagrangian. Or anybody's Lagrangian will be like this in 3 dimension. R is 3-dimensional vector, V is also 3-dimensional vector, and T is time in general. So this is the possible Lagrangian for anybody in 3D. Okay. You could have written also x, y, z, vx, vy, vz, because it is 3 degrees of freedom. So there will be 3 coordinate x, y, z. But let me write in terms of r, v, and t. Okay. So now in for a free particle also Lagrangian should be like this, and we want to construct this Lagrangian. So free particle has certain properties. First is the homogeneity of space. Homogeneity of space means space is homogeneous. So if the motion of a free particle, that particle moving in a particular direction all the time with the same speed, does not depend where you have the coordinate axis. Coordinate axis is at 0, 0, 0, or your coordinate axis is 1, -1, 0, or ABC, where ABC. It does not depend on the coordinate axis. So this is called homogeneity of space. Means space is homogeneous. I am considering my coordinate axis to calculate this R is the origin 0, 0, 0. Or I can consider my coordinate axis as ABC, some ABC, arbitrary values of ABC. It does not matter. The free particle will move with a constant speed all the time. Whether you have a coordinate axis with origin as the origin at 0, 0, 0, or you have a coordinate axis with ABC as your origin. Okay. So this is called homogeneity of space. So this immediately means that R, the value of R, so So the Lagrange, that means I can make a coordinate shift r prime going to r plus say a. This is my shifting of coordinate. My position vector was r. Let us define a new position vector r prime with respect to shifting. So homogeneity of space means that this will be the symmetry of the system. That under this transformation, Lagrangian will not change. So under this transformation, but if your Lagrangian depends on r, and if I make this transformation, my Lagrangian will change. So first properties I said homogeneity of space, because particle moving with a constant speed in a particular direction all the time will not affected by this transformation. So this because the homogeneity of space. So then this Lagrangian will not change under r prime going to r plus a. That means this L must be independent of r. So I started with a Lagrangian, most general Lagrangian, this in 3 dimension. Then I argue that okay, for a free particle space is homogeneous, so Lagrangian should not depend on r. If space is homogeneous, it should not depend on the r. So now with the first properties of this system, I found that okay, Lagrangian will be function of v and t in this case for free particle. Now we'll discuss another properties. Okay. See, now homogeneity in space. Now second properties I am going to discuss is homogeneity in time. Now space I have already discussed. Now homogeneity of, what is the meaning? I am looking at the particle at 10 o'clock. Right now it is 10:35, or after the class at 11 o'clock, or maybe 1 o'clock. I'll have the same dynamics. Particle is moving with a constant speed in a particular direction. This I'll have any time I look at the system. So there is no change in the dynamics with time. I'm looking at 10:35. I saw the particle moving with a v velocity. I'm looking, this is a free particle, no force acting on it. Particle, according to Newton's first law, particle will move with the same velocity unless otherwise it is restricted by a external force. So now somebody look at the same particle at 11 o'clock, it will, the particle is moving with a v velocity in x direction, say. Somebody look at the afternoon, 5 o'clock, this same particle is moving with this velocity. So it does not depend on time. So homogeneity of time means that t prime going to t plus c, I change time 10 o'clock to 11 o'clock, 11 o'clock to 12 o'clock kind of thing, then does not depend on this. So Lagrangian L should be independent of t. Lagrangian for a free particle cannot depend on time. So now my Lagrangian has, after the second properties, my Lagrangian is changed now to only function of v. Now third properties I'll be using isotropy of space. Okay. Isotropy of space. Isotropy of space meaning what? Let me explain it. For a free particle, its dynamics does not depend whether I have a coordinate axis like this or whether I have a coordinate axis, rotated coordinate axis. I can have this, I can have this as a coordinate axis, dotted line. So if I make a rotation about my coordinates xyz, dynamics will not change. Dynamics is the same, it's moving in a with the uniform speed. So angle, direction, so if the for a free particle, space is isotropic. Isotropic means rotational invariant. So if space is isotropic, that means rotational invariant. Even L cannot depend on V. V has a vector sign, so it cannot depend on the vector V. So after the third properties, L should be function of mod V. Only the magnitude, only the L should depend only on the magnitude. Or this also we can write L is function of V square. V mod V is root over V square kind of thing. So mod V I write this is similar. Okay, so conclusion after the three properties of a free particle system. Free particle system is homogeneous in space, homogeneous in time, and isotropic in space. I restrict my Lagrangian, I argue that my Lagrangian from possible this most general dependence to it is now depend on L is function of. So do you have any question? This is a now I'll change my gear to something else. So first we argue that a free particle has, if you have a system of free particle, it does not depend on the R prime changing to R plus C. This is called translational invariant. This is called translation in time. Does not depend whether it is at 10 o'clock, 11 o'clock or 5 p.m. It also does not depend on the angle, rotational invariance. So from these three properties, I restrict, it does not depend on R, it does not depend on T, it does not depend on the direction of the velocity. Okay. So it depends only on the magnitude of the velocity, so we write V square. Now let us consider two inertial frame. This is S prime, this is S. This inertial frame is moving with a small velocity epsilon, and the Lagrangian according to observer of this frame is V square. So Lagrangian according to this frame will be V prime square, where V prime will be your V plus epsilon, right? Because this S prime frame, also inertial frame, is moving with a small velocity epsilon. Epsilon is a small velocity. Okay, so now the Lagrangian as observed, but they are inertial frame. Equation motion should be same. So let me write, but equation of motion will have same form, covariance. So I think you know covariance and invariance. So equation motion will have the same structure in both the frame. So we expect that these Lagrangian should be related, or we should use the properties of Lagrangian to ensure that equation of motion will have the same form. Okay. So now let us see. So what I'll do, I'll make a Taylor series expansion in the second Lagrangian, L prime frame. Okay. And we want to see. Okay. So now, so L V plus epsilon whole square, this is the Lagrangian in S prime frame. So we are starting with that. So this can be written as V square plus 2 V dot epsilon, right, plus epsilon square here. But I am neglecting the epsilon is small, so I am neglecting epsilon. So this. Now this I will expand as a Taylor series. So it will be function of V square. Then there will be del L del V square times 2 V dot epsilon plus order epsilon square. I am neglecting higher order term. Clear? This is a Taylor series expansion. I hope you know the Taylor series, right? If you know that if you have x plus alpha, then it is f of x, then del f del x x minus alpha alpha. Okay, here actually I make around okay, this will be alpha because I am expanding alpha equal to 0, around alpha equal to 0, here also around this. So first term will be alpha equal to 0, so first term will be fx, then del fx del x alpha equal to 0 times alpha, then alpha square by 2 del 2 f del x square, but alpha equal to 0 and so on. So, but I am higher ordering, so this is Taylor series expansion and you are familiar with this. Now look at this. Now recall the properties of Lagrangian such that these two Lagrangian L prime in my earlier notation, L prime V plus epsilon whole square will be V square plus this. So what will be this term such that L and L of V and L of V prime will have the same equation of motion. So this will have same equation of motion because laws of motion will be covariant in all inertial frame. This is the thing you know from your special theory of relativity. Inertial frame, you also know concept of inertial frame. It is a very much imaginary quantity, hypothetical quantity, inertial frame. There is no real example in fact, but I think you have a knowledge about it. If you have difficulties, let. Now, what will be this term? Such that this whole term such that it will be the three properties we know L prime going to L prime L plus C, L prime going to C of L, or L prime going to L plus df dt. So if I have any of these properties between these two Lagrangian, then I'll say that this equation of motion will be the same. Dynamics will be same and equation motion will have same form. So if I this is not possible del L del V square because I want to know how L depends on V square. So suppose one possibility is suppose del L del V square equal to 0. This is the easiest possible. That then it will be L prime equal to L. So they will give you the same equation of motion. But what does it mean? I said my Lagrangian depends only on V square. Now I am saying that my Lagrangian is independent of V square. That means my Lagrangian is constant. But that is trivial thing. Lagrangian is constant means no equation, no dynamics, right? So that is a trivial case. So let me write this is trivial situation. Trivial situation, and Lagrangian is constant. Now next possibilities. Next possibilities is del L del V square equal to constant. It is 0. If it is not 0, then it will be constant. Constant is possible. So if it is constant, then what is happening? Then your L prime, that is the this is also, let me write L prime. So L prime equal to L plus, now this is constant, so 2C V dot epsilon. Epsilon is constant vector, so I can write L plus ddt of F. This I can write, where F is 2C R dot epsilon. If your F equal to 2C V in place of V, I wrote R dot epsilon. So dF dt will be 2C V dot epsilon. R dot means V dot epsilon. Epsilon is constant. So if I have this, then I can have that these properties, we can have same equation of motion. So immediately I can say that Lagrangian is a linear function of V square. Linear function means when you differentiate first derivative, it will give you constant. So now I find my Lagrangian. I got an idea of my Lagrangian of free particle. So that means my Lagrangian is L equal to C V square. Then only del L del V square will be C. Now what will be the equation of motion? Free particle equation of motion. Free particle equation of motion is mv dot or ddt of mv is 0. This is the equation of a free particle. Rate of change of momenta is 0. No force. That is a free particle. So let us now use Euler Lagrangian equation. Ddt of del L del V square minus del L del R equal to 0. This is my Euler Lagrangian equation. But this is already I have seen is 0 because homogeneity of space. So space is cyclic. Here R is cyclic. Okay. R is cyclic. Another example. Here R is cyclic. Okay. So ddt of mv square. But now what is your L? L is this. So ddt of v square means 2 no ddt of v. I'm sorry. This is Lagrangian equation is not v square, but Lagrangian equation is v. Okay. So it will be ddt of 2cv to 0. So what will be the c such that I get this equation? So 2c should be m. So 2c should be m. So if we choose c equal to m by 2, then I get the correct equation. This equation and this equation will be same. So from here I conclude that Lagrangian for a free particle is, oh no, stupid. Lagrangian for a free particle is L equal to C equal to m by 2. So half m square. That means kinetic energy of the system. So Lagrangian of a free particle is nothing but the kinetic energy of the system we obtain. Good. So now, if the particle is not free, what will happen? That we are going to tell you. if this particle is not free, then what will happen? Okay. ddt of mv equal to 0. So free particle ddt, that means force, rate of change of momenta equal to 0. For a conservative force, now particle is not free, but there is a force acting, and that is the conservative force. Then the equation of motion is ddt of mv equal to minus del u del r, right? Or if it is one dimensional, x dot, and this is r, because it is a. So immediately I can see that my Lagrangian will be then half mv square minus u. U is the potential energy. This is just verifying from back. Let me repeat this. This is important, and I'll show that how. Let us make a backward calculation. So backward calculation means, suppose this is my Lagrangian. So what will be the equation of motion? Equation of motion ddt of del L del V minus, this is u function of r. Conservative system, so only function of r. Del L del r equal to 0. This is my equation of motion. Euler Lagrangian equation of motion. So now what will happen? I find from here, this is ddt del L del V, del L del V will be mv. So this will be mv minus del L del r. This is not depend on r. So this, so minus this minus, and there will be a minus. Okay. So plus del u del r equal to 0. That means ddt of mv equal to minus del u del r, where u is the potential energy. So now we find that, okay, for simple system, your Lagrangian is kinetic energy minus potential energy. Okay. But this may not always true. In most cases, Lagrangian is T minus U, kinetic energy minus potential energy. But remember, with the lead ink I have written, may not be always true. There are systems where Lagrangian are not kinetic energy minus potential energy, but something else. Only requirement is that Lagrangian should, so this you remember, Lagrangian should produce the correct equation of motion. This is the requirement for my Lagrangian. Lagrangian should produce correct equation of motion. This is not the always, this statement is not always true that I wrote. For example, I'm giving you a homework problem that if you have a relativistic particle, free particle, say relativistic free particle. I'll stop in 3 minutes. So if I have a relativistic particle, so write its kinetic energy. Kinetic energy will be gamma minus 1 m0 c square, right? This is the kinetic energy of a relativistic particle. So if it is a relativistic free particle, and then it's supposed to be Lagrangian is gamma minus 1 m0 c square. Gamma is gamma, you know, gamma is 1 over 1 minus v square by c square, right? This you. So this will be the supposed to be Lagrangian, but this is not correct. So please verify that for relativistic particle Lagrangian is not T minus U form. Lagrangian for so this is a kinetic energy. From kinetic energy you calculate your equation of motion, and you will see that it is not the equation of motion of a relativistic particle. Okay. So this relativistic free particle Lagrangian is m0 c square root over 1 minus v square c square. So this is the Lagrangian for a relativistic free particle. Now in next class on Saturday, Friday class I think Krista will take. If he cannot take, then I will take. Friday I have another class, so generally I avoid that class. But if I'll ask Krista to take, if Krista cannot, then I'll take. Our Saturday class, I'll now I'll consider simple system like pendulum, double pendulum, mass spring system, etc., and we'll construct the Lagrangian. So in this course, you have to learn very well that how to construct the Lagrangian. Okay. Now, do you have any question? Otherwise, my class is over. And I found that we started around 45, 50 students. Now it is 33 students. So those who are leaving, I'll keep an account of them. Those who are leaving, already I know some names who are leaving. Don't say that I have network problem. Nowadays, nobody has network problem. Okay, so I'll not accept that network problem, but students live in that. People can live in my class. I don't have any problem that students live in my class, but they cannot say that they live because of their network problem. They should accept that I say I am not attending your class. That they have to accept.
Sir, which book have you referred for this part?
Sorry?
So you have referred which book for this part?
Okay, for this part, Landau-Lipschitz mechanics.
Okay, sir.
But some other books also you can get, but Hamilton's principle, generalized coordinate, Hamilton's principle, Euler-Lagrangian equation, this part certainly from mechanics book. Almost everything I took from there. But try to follow I'm going very slow, try to follow in the class and try to ask in the class, get your doubts clear in the class. Any other question?